Alright, what's up everybody? It's Professor B and I'm back today with some material science concepts. So we're gonna hit the ground running with a simple problem. It says, part A says, give the silicon lattice parameter, which is A equals 0.53 nanometers. Calculate the number of silicon atoms per unit volume. So you can think you can think about this as there is like you have a room and there's 5 people in the room. So each of these persons are going to occupy a certain amount of volume. So that's what we're going to find. We're going to find the volume that one of these silicon atoms occupies in its structure. So we know that silicon has a diamond structure, as we can see here. And so we know that the number of atoms per unit volume is equal to the number of atoms in the unit cell divided by the volume of the unit cell. So if we think about a cube, right? We have a cube. That's a messed up cube, but if we think about a cube like this, we know, okay, so in 2D, we know that the area is going to be this times this, right? A times B, that's going to give you the area. But if we think about the volume of a cube, it's going to be this length times this length times this length. So we're given what A is. We're given that A is 0.543 nanometers. So that's A, and that's A. So A cubed is going to be the volume of the unit cell. And the number of atoms in the unit cell, well, from the table, from a given table, we know that the number of atoms in a diamond structure is 8. And we divide that by the volume of the unit cell, which is A cubed, and it's 0.543 nanometers cubed. So the number of atoms per unit volume is going to equal, if you put that into your calculator, you're going to get 49.9678 atoms per cubic nanometers. And that is going to be the volume that one atom occupies. Okay? So now we go to part B. And part B tells us, let me see if I can move this. So part B tells us calculate the number of atoms per square meter and per square nanometer on the 100 plane, which is this plane right here, and on the 110 plane, which is the plane that's diagonal, and on the 111 plane, which you can see forms an equilateral triangle. Right? So planes in the silicon crystal as shown in this figure, and we want to know which plane has the most number of atoms per unit area. So keep in mind that before we were calculating volume. Now we're going to calculate area. So let's start with the 100 plane. So for the 100 plane, again, we know that our lattice constant is 0.543 nanometers. So we're thinking about this in 2D, right? We have this is the plane right here that's with dashes, and we have one atom here, another atom here, another atom here, and another atom here, and one here. Right? So again, the number of atoms in this plane is going to be 1. And then this circle is cut So we don't think about it as a sphere. We think about it as a circle in 2D, and it's cutting 1/4 of the circle of the atom, circle the atom in 2D. So we would have 1/4 times 4. So we'd have 1/4 times 4 of these plus 1. This is going to give you 2. So we're going to have 2 over a squared, because they want us to find the atoms per square meter. They're referring to area here. So then we would have 2 over 0.543 nanometers squared, and that should give you 6.7831 atoms per square nanometers. That's for the first plane. Now if we calculate the second plane, again, we're going to find the number of atoms in this plane. So we have is a diagonal, right? We have a diagonal plane. So again, we're thinking about this in 2D. So we have a diagonal plane where we have one atom here, another here, another here, on the bottom, on the bottom, on the bottom, and then we have 2 in the center. So we're gonna have one-fourth, because these atoms are being, by the plane, they're being cut off just 1/4 of the circle. So 1/4 times 4 plus these 2 plus these are being cut off by half times 2. So we should have 1 plus 2 is 3 plus 1 is 4. So the total number would be the total number of atoms in this plane would be 4. So we would have 4 over the area. So if we think about this, the area of this rectangle, right? The area of this rectangle is going to be the length of the diagonal times the height. So it's going to be this length times the height. So the way that we can find this length right here would be, so if we look at the very bottom, it forms a square, and this plane is cutting straight through it diagonally, right? So it's cutting straight through it diagonally, and we know what the lattice constant is. They're giving us the lattice constant, the lattice parameter, which is from one corner to another. That's what A is. So we have A, and we have A, and we would like to know what this distance right here is going to be. So let's just call that distance C. Whoops, I didn't mean to do that. Right, so essentially what that forms is a triangle. So using the Pythagorean theorem, we have C squared is equal to A squared plus A squared. So then we have C squared is equal to 2A squared, and then taking the square root of both sides, we would have A square root of 2. So that is going to be the length of the diagonal, right? So for our area, we're going to have A square root of 2 times the height. And what is the height? Well, the height is just from one corner of the atom to the other. That's all that is. So that's just going to be times A. So the area is going to end up being A squared square root of 2. So now that we have the area, we can find the number of atoms in this plane. The number of atoms on the plane. So we have 4. We know that there are 4 atoms on the plane. And the area, which is a squared times square root of 2. And what is a? Is going to be the lattice parameter, which is 0.543 nanometers squared times the square root of 2. So that should give us 9.5928 atoms per square nanometers. And that's for the 110 plane. So let's move this down and let's try to do the next plane. So for the plane 111, we see that, well, first let's calculate the number of atoms in this plane. So we have a equilateral triangle where all the sides are the same, right? And we have an atom here, another one here, another one here, another one here, another one here, and another one here, right? So we know that these 3 right here, we're gonna do it in red. So these ones are being sliced in half. So 1/2 times 3 of them, right? Plus, and these ones right here are, you can think of it as being a cut off like a pie. And this is going to be, so this slice that the triangular plane is cutting, it's going to be 1/6 of the 3 atoms. So the total is going to be 3/2 plus, I think that's 1/2. So which is 1.5 plus 0.5, which is going to give you 2. Right? So that's going to be the number. That's going to be the number of atoms in the plane. It's going to be 2. So now we need to find out what the area of this triangle is going to be. So like I said before, all these sides are the same, and we know that the area of a triangle is equal to the square root of 3 over 4 s squared. Now, again, what is going to be the length of S? Well, we see that the base of the triangle is cutting diagonally straight through the bottom face of the cube. So again, we want to know what this distance is, and we know what A is. We know what A is. So using our Pythagorean theorem, we know that C is equal to A square root of 2. And C, well, in this case we called it S, right? We called it S. Let's call it S. So this is that's what S is. So if S is the bottom base of the triangle, and if all the lengths are the same, then S is also going to be this length and this length as well. So my area is going to be A square root of 2 squared. And canceling, we're going to have the square roots cancel, so we have 2. And then the A is squared, so we have 2 over 4, which is square root of 3 over 2. Whoops, there's some bad handwriting. It's going to be square root of 3 over 2, A squared. So now, to find the number of atoms in the plane, we're going to do 2 over the square root of 3 over 2 times the lattice parameter, which we said was 0.543 nanometers squared. After putting that in your calculator, you should get 7.8325 atoms per square nanometer. So if we go back to the question wants us to find which plane has the most number of atoms per unit area. So we're in 2D. So we know that the 111 plane has 7.8 atoms. We know that the 110 plane has 9.5 atoms, and the 100 plane has 6. So the plane that's going to have the most atoms per unit area is going to be the 110 plane. Now, let me move this down a little bit so we can continue with part C. Now, part C says the density of silicon dioxide is 2.27 grams per cubic centimeters. Given that its structure is amorphous, calculate the number of molecules per unit volume in cubic nanometers. You want to compare your result with A and comment on what happens when the surface of the silicon crystal oxidizes. So the atomic masses of Si, of silicon, and oxygen are 28.09 and 16, respectively. So, one would think, we know that density is equal to mass over volume, and we want to find out what the molecules are per unit volume. So we're not necessarily going to be using this equation. This is merely just a conversion. Given that the density, rho, is 2.27 grams per cubic centimeter, we want to go from this to moles. So we're going to divide by the molar mass of SiO2, which is going to be the atomic mass of silicon is 28.09 plus 2 times 16. That should give you 60. Whoops, what happened there? That should give you 60.09 grams per moles. So then we divide the density by the molar mass, and we'll have 60.09 grams per moles. And that should give us, the grams cancel out. So when we do that, that should give us 2.27 over 60.09 moles per cubic centimeter. Now we want to go from moles to molecules because we want to find out the number of molecules per unit volume in cubic nanometers. We'll get to that. But we want our moles to cancel out. So using Avogadro's number, which is 6.023 times 10 to the 23. Avogadro's number could be anything. It could be atoms. It could be donuts per mole. In this case, we want to know the molecule. So molecules per moles. So my moles cancel out. And we should get, after you put this into your calculator, we should get 2.2753 times 10 to the 22 molecules per cubic centimeter per volume. Now, we want to go from this to nanometers. Let me just write that very well. Molecules per volume. So we know that 1 centimeter is equal to 10 to the negative 2 meters, and we know that 1 nanometer is equal to 10 to the negative 9 meters. So we want our centimeters to cancel out. So we're going to use this one right here. And we're going to put our centimeters on the top and our meters on the bottom. And we have to, and in order for these two to cancel out, we're going to have to raise this to the third power. And the units here should cancel out. Now we want to go from molecules per cubic meters to molecules per cubic nanometer. Per cubic nanometer. Right there it says per cubic nanometer. So we know that 1 nanometer is 10 to the negative 9 meters. So of course we want our meters to cancel out. So we're going to put our meters on the top and our nanometers on the bottom. And again, we're going to have to raise this to the third power so that our cubic meters, so that the unit of our cubic meters cancel out. So after putting this into your calculator, you should be left with 22.753 molecules molecules per cubic nanometer. And then it says compare this result with A and comment on what happens when the surface of an Si crystal oxidizes. So if we go back to A, we basically have a density of 49 atoms per cubic nanometer. And here we have 22, so we can say that the surface of the Si crystal, we're comparing what's happening with the surface of the Si crystal as it oxidizes. It's becoming less dense. Because you can say that oxygen takes up more space, and I guess it causes more stress on silicon. So that would be our answer for part C.